Hello students, welcome to solid state physics class today. It comes under semester 5 and paper 6A. I am N. Chandana, assistant professor of physics from Government Degree College, Khartaban. A quick recap we will be having now. So let us recap what all the things we have studied in the previous class. The elements of symmetry we have learned. What all those? Axis of symmetry, planes of symmetry and center of symmetry we have learned. And we have seen an example for cubic crystal lattice structure. Then we have learned the 7 crystal systems we have. That is CTO or HMT. I asked you to learn in that fashion. That is cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. Then we have Bravais space lattices. So we told that we have been told that 14 ways we have arranged the similar way where the lattice point has the same environment surrounding that lattice point. But for a cubic system, for a cubic crystal system, we have in particular only 3 ways of arranging in that fashion. That is simple cubic, body-centered cubic, and face-centered cubic. That we have learned here. Then the lattice points per unit cell. Now let us see for a simple cubic crystal structure. So what would be the lattice points per unit cell? Now for a simple cubic crystal lattice, let us see. There is one lattice point at each of the 8 corners of the unit cell that I have told you in the previous class. See here, as a cube has 8 corners, at each of the corner of the cube we have one atom, single atom. So all the corners we have sum up to 8 corners. 8 corners we have. So how much I will get? 8 into 1 by 8. So this single lattice point will be common for, it is sharing its part to other 7 unit cells. So other 7 unit cells plus this unit cell comes 8 unit cells. So each and every single corner atom will be shared among 8 unit cells. See here, 8 are surrounding unit cells. That is the reason the number of lattice points per unit cell can be written as 1 by 8th part into 8 corners. So I get 1 lattice point per unit cell. Okay. So 1 by 8 into 8, that is 1 lattice point per unit cell we have here. This is a simple cubic system. So students, you have to learn here one trick, that each and every lattice point is sharing among 8 similar unit cells, surrounding unit cells. Okay, that is the reason we write 1 by 8th part. See, if you take a pizza, let us suppose this is a pizza, and 3 people are sitting here. Yourself, and you have 2 friends. So you 3 people are sitting there to have a pizza. So what do? You want to have an equal amounts of pizza between you 3 of you. So what you'll do? How you cut it such that each of you get equal amount of pizza. So if I suppose these 3 parts are equal, so how do you do? So each of you, how much did you get? One third of the pizza. So 1/3 of pizza into how many of you are there? 3. So that gives you 1 pizza. Okay. So similarly here 1 by 8th of 8 gives you 1 lattice point per unit cell. Next, let us see for face-centered cubic lattice. So for a face-centered cubic lattice, what do we have now? Let us see. The name itself, sorry I didn't write here, FCC. FCC. The previous one is simple cubic lattice is SC. Okay, SC. The other one is FCC, face-centered cubic lattice. Here each unit cell consists of 8 corner lattice points, same as that of simple cubic. So the same simple cubic thing we'll write here. So at the each of the corners we have one atom. It is shared among 8 surrounding similar unit cells. Hence, we get 8 into 1 by 8. So 1 by 8 part is there for our unit cell now. So 8 into 1 by 8 we get 1 lattice point. Then there exists 6 here atoms sitting at each of the faces of the cube. How many faces are there for a cube? 6 faces. Faces, F-A-C-E-S. So I'll surround it with green, the face-centered atoms. This is the face-centered atom. So we have in total how many are there? 1, 2, 3, 4, 5, 6. So 6 face-centered atoms we have. This face will be common for the upper cube. If you take a cube, if you take a plane here, we draw a plane here in this way. Okay. And again, this is a cube here. Okay. And this is also a same cube. Again, I'll have lattice points here, atoms sitting here. Okay. So again, I'll have a face-centered atom here, face-centered atom here, a face-centered atom here in this face, and also a face-centered atom here. That means the face, what is that face here? And again, the face-centered atom here, face-centered atom to the other one here. So 6 atoms. So this phase atom here, this face-centered atom of our bottom cube will be the same as bottom unit cell will be the same for shared among this unit cell and this unit cell. Okay, top one and bottom one. This phase atom. That means it is shared among 2 unit cells. So each and every face-centered atom is shared among 2 unit cells, right? So we can write it as 6 face-centered atoms is shared among 2. That is half part will be shared among these 2 unit cells. Will gives you 3. Okay. Here corner atoms, because of corner lattice points, what did you get? 1 lattice point per unit cell. Because of 6 phase lattice points, each being a member of 2 cells, we got 3 lattice points. So how many total number of lattice points per unit cell are there now? You tell me now. So total is 3 plus 1, that gives rise to 4 lattice points per unit cell here. Okay. 4 lattice points per each unit cell here. I'll go to the previous slide. Here 1 atom per each unit cell. 1 atom, or else I can take it as 1 lattice point per each unit cell for a simple cubic. This is for face-centered cubic. Okay. Next comes body-centered cubic. So in a body-centered cubic lattice, that means this is BCC. This is BCC. In body-centered cubic lattice, what type of things we see here? Same as simple cubic, we have a simple cubic system. Each corner we have an atom shared among 8 surrounding unit cells. So we have 8 corner atoms here in this way. Then there is a single atom sitting here at the center of the body, center of the unit cell here. Center of the unit cell. If you observe, this is not shared between any of the surrounding unit cells. This lattice point is not shared among any of the unit cells surrounding this unit cell. Hence, this can be treated as 1 lattice point per unit cell, and again the same as before, 8 lattice points we have at 8 corners of the cube, which is shared among 8 surrounding crystals. So each of the atom is shared among 8 surrounding unit cells. That is the reason 8 into 1 by 8 we get 1, and the body centered atom will be 1. So finally I'll get 1 plus 1, I'll get 2. So number of lattice points per unit cell here is 2. The number of lattice points per unit cell in simple cubic is 1. When coming to face centered cubic, it is 4. Coming to body centered cubic is 2. Okay. Now you have to draw all these 3 diagrams. You have to learn. Here 8 corner, we have 8 atoms kept at 8 corners of the cube, simple cubic. Then here you have to draw 3 planes. You have to draw 3 planes exactly. You have to draw here 3 planes exactly, making half the x-axis, half the y-axis, half the z-axis. 3 perpendicular directions. And at each of the center of each face, we have a single atom. Okay. So 6 into 1 by 2, 3. 8 into 1 by 8, 1. Hence we get 3 plus 1 is 4. Body centered, 8 corners, 8 atoms. But at the center, we have single atom here. This is the diagram for body centered cubic. Next, how do we calculate lattice constant? What is lattice constant? Let me tell you. Lattice constant is nothing but it's one of the parameters of determining lattice constant is one of the parameter which describes the axial lengths of a crystal lattice. So for a cubic crystal, what would be it? A equal to B equal to C. All are equal. All axial lengths are equal. So hence we can take it as A. I took it as A. Lattice constant is A. For my cubic structure, constant is A. Density of the crystal is rho, if I suppose. Density is mass by volume. So now volume of the unit cell will be A cube. Okay. A cube with A is the axial length, or edge of the cube is A. Because in cube all sides are equal, A is equal to A is equal to A is equal to B equal to C, that is A. Then volume of the cube will be A cube. That is nothing but here volume of unit cell. Mass of unit cell will be density into volume. Since density is equal to mass by volume, mass equal to density into volume. Hence I got mass of each unit cell is rho A cube. Let us consider that there may be n molecules or n lattice points per unit cell. M is the molecular weight and n is the Avogadro's number. Then what would be the mass of each molecule? M by n, molecular weight by Avogadro's number. Mass of each molecule. But here I say that there are n molecules. Okay. So n into m by n will be the mass of each unit cell. Okay. Now what happens? Now let us consider that mass of each unit cell rho A cube will be the first equation. Mass of each unit cell equal to n into m by n will be the second equation. Now comparing equations 1 and 2, we can equate them. Since both are mass of each unit cell, so rho A cube is equal to n into m by n. We bring this rho on the other side. So it will be dividing now nm by n. Then A is equal to nm by rho n whole power 1 by 3. Nm by rho n whole power 1 by 3. There will be problems coming out with this formula. They will ask you to calculate the lattice parameter of a single crystal, simple cubic crystal system when given the molecular weight and rho density of the unit cell they'll be giving you. So and we can easily identify. What is n? Number of lattice points per unit cell, as I told you. Now for a simple cubic, how many lattice points are there for unit cell? We can write here the formulas. Now let us write. So for a simple cubic system, we have A is equal to n is 1. So 1 into m by rho n, 1 into m by rho n, okay, whole power 1 by 3. Okay, this is for what? Simple cubic system, because number of lattice points is 1. For a body centered cubic, we have lattice points 2. I will replace n by 2. For a face centered cubic structure, number of lattice points are 4. So I will replace n by 4. So 4m by rho n whole power 1 by 3. In this way, we can calculate the lattice parameter for different types of cubic crystal systems by using this formula. A is equal to Nm by rho n whole power 1 by 3. Similarly, if he gives a lattice constant then and asks us to find out the molecular weight of that substance, we can easily calculate the material by using this formula. A is equal to Nm by rho n whole power 1 by 3. Next comes Miller indices. So what are these Miller indices? Miller indices. So Miller is a scientist. It was named on his name. What are Miller indices? Miller indices are nothing but they're simple numbers used to designate a plane in a crystal. So we already learned what is a lattice plane. So in order to designate a plane in a crystal, we use these three numbers, set of three numbers called Miller indices. Okay. What are these Miller indices? How they are defined? One of the most prominent definition I have put for you here. They are the reciprocals of intercepts with which the plane makes with the axis. Here the axis means x, y and z axis when reduced to the smallest numbers. Okay, they are the reciprocals of the intercepts which the plane makes with the axis. If you consider a plane which you want to designate, okay, you take that plane and you calculate the intercepts first. And then you take the reciprocals of the intercepts. Then the obtained reciprocals of the intercepts in terms of whole numbers, you will find out the Miller indices. Let us calculate. Let us see the steps, the three steps which we have to follow in calculating the Miller indices of a given plane. Rules for finding Miller indices. Here I have written here for you. Rules for finding Miller indices. Step 1 is what? Determine the intercepts of plane on the 3 coordinate axis. Determine the intercepts of plane on the 3 coordinate axis. As we have discussed, we have to determine the intercepts of the plane on the x, y and z axis. Then step 2, take the reciprocals of these 3 intercepts. Then step 3, we have reducing these reciprocals into whole numbers. Okay. Let us give one example. Actually, I have given one example for you all. Let us see this plane. See, this is a plane here. In the right side, you have to see in this diagram. See here in this diagram. This is the plane. This is the plane which is intersecting x-axis, z-axis and y-axis here. This plane is intersecting x-axis at 2. So what is the x-intercept? 2. Similarly, on y-axis at 3. What is the y-intercept? 3. Similarly, on a z-axis at 4. So here it is 4. So what shall I write now? The intercepts of the plane intersecting on x, y and z axis are 2, 3 and 4. 2, 3 and 4. Here 2, 3 and 4. This is step 1. We got intercepts now. Now what is the step 2? We have to take the reciprocals of this intercept. So first reciprocal is 1 by 2, second is 1 by 3 and third one is 1 by 4. Third step is we have to reduce the reciprocals into whole numbers. It means we have to reduce these reciprocal numbers into whole numbers. You know now what is the LCM of 2, 3 and 4? That is 12. So what would be the LCM when I take with these things and I'll obtain that figure? Here 6 because 6 2 is 12. Here it is 4 because 4 3 is 12. And here it is 3 because 3 4 is 12. So finally I'll obtain the Miller indices as 6, 4 and 3 for this plane. This plane. The plane can be written as in brackets 6, 4 and 3. There is no requirement of commas here. You can write in brackets, open brackets 6, 4 and 3. So these 3 steps we follow. For any plane they give in your exam, we can calculate the Miller indices. Okay. Similarly, if they give you the Miller indices, we should be able to draw the plane corresponding to these Miller indices in the crystal plane. we should be ready to draw the plane corresponding to these Miller indices. What you'll do? You'll do the reciprocate system. What you'll do? First, I have given you Miller indices 6, 4, and 3. I have given you the Miller indices 6, 4, and 3. Okay, given you the Miller indices what? 6, 4, and 3. Okay, now what I'll do? Well, I asked you to draw the plane. I asked you to draw the plane. Okay, then what you'll do? First, will calculate this Miller indices 6, 4, 3. I already given you. You'll do reciprocation. First, you take LCM and then you do the reciprocation. Then you get 1 by 2, 1 by 3, and 1 by 4. Okay, then you do again the reciprocation. What you'll get? 2, 3, and 4. So we obtained intercepts 2, 3, and 4 from Miller indices 6, 4, and 3. Now we have to draw these intercepts on your diagram. So we have to draw a plane which intersects x-axis at 2, y-axis at 3, and z-axis at 4 as shown in the figure. Then we will obtain this plane. In exam, either way they can ask you. So be alert and you understand how to answer and give the answer in your exam. Okay. Now let me go to the next slide. This is in this way we can calculate the Miller indices. So here I am showing you some of the Miller indices of some planes, the random planes. This is 100 plane here. See, 100 plane. That means Miller indices are 100. Miller indices are 100. That means how should be the plane? The plane should be there in YZ. The plane is in YZ plane. So for a YZ plane, what would be the intercepts here? I'll write here. X-intercept I have 1. See here. It is cutting it. This is unit I'll take. X-intercept is 1. For a YZ plane, Y-intercept is infinity and Z-intercept is infinity. So these are the intercepts. First step. This is the first step. What would be the second step? Take reciprocals. So 1 by 1 is 1. 1 by infinity is 0. 1 by infinity is 0. Okay. So this is the second steps. I got reciprocals. Now I'll take LCM. And what I'll get again? 100. So this is nothing but my HKL. Parameters HK and L. Okay. So this is the plane corresponding to a plane parallel to YZ axis. Plane YZ plane which is intersecting x-axis at 1. Similarly, we can write a plane parallel to here xz axis, plane parallel to YZ, and here 110 plane. This is a diagonal plane, as we have learned in your axis of symmetry, planes of symmetry. There I have told you diagonals, planes of symmetry. So this is such a case. And here see this plane, it is intersecting 1 on x-axis, 1 at 1 on y-axis, and at 1 on z-axis. So this plane comes out to be 111 plane. The Miller indices are 1, 1, and 1. Okay. Now we'll go for interplanar spacing. So what is interplanar spacing? The spacing between any two successive planes, two successive lattice planes. Okay, the distance between any two successive lattice planes is said to be interplanar spacing. It is denoted by DHKL. It is denoted by DHKL, small DHKL, where HKL are Miller indices. So simple structure we'll take for a simple cubic system. Okay, like cubic tetragonal or orthorhombic crystals, we know that for them alpha is equal to beta is equal to gamma is equal to 90. For such type of systems, for such type of tetragonal and cubic and orthorhombic systems, equal to beta equal to 90. What is the DHKL formula? We can obtain the interplanar spacing by using this formula. DHKL 1 by root h square by a square plus k square by b square plus l square by c square. Here see, h is nothing but the plane HKL plane, and a, b, c are the, what are all those? They are called the lattice parameters. Okay, axial lengths. In this way, we can calculate the interplanar spacing between any two successive lattice planes of a cubic or tetragonal or orthorhombic by using this formula. Okay. So far we have learned many things today. So thank you so much. So let me revise once. So let us go back for 2 minutes. We have learned what are the lattice points, how many lattice points are there per unit cell for simple cubic structure, for face-centered cubic structure, and body-centered cubic structure. And then we have calculated the lattice constant for a cubic crystal lattice. That is A is equal to Nm by rho n whole power 1 by 3. And then again we have discussed about Miller indices. How do we calculate Miller indices in 3 consecutive steps we have learned. And I have given even one example. And in vice versa, we can calculate now either from Miller indices to a plane or else from plane to Miller indices we can obtain. Then Miller indices of few planes which we have learned here. Then we have come for interplanar spacing between successive lattice planes of a given cubic or tetragonal or orthorhombic crystals. We can calculate directly by using this formula. DHKL is equal to 1 by root h square by a square plus k square by b square plus l square by c square. When it comes to cubic structure, we know that A is equal to B equal to C, right? So when I substitute A is equal to B equal to C, I directly get DHKL equal to A by root h square plus k square plus l square. So thank you so much, students. Let see you in the next class. Thank you so much for your patient listening. All the best.